Hello there. All right, so I'm going to look at an example similar to 3a on the worksheet, on the functions 1 worksheet. All right, so you'll notice that the function goes from n cross n to n being the natural numbers. All right, so before I fill out the table, I just want to talk a little bit more about about n cross n, what that looks like, and how you can visualize what that looks like. All right, so let me go down here and give myself a little more room. Okay, so first thing is remember that if you have two sets, A and B, let's say A and B are sets, that A cross B is the set of ordered pairs X, Y, such that X is in A, Y is in B. So n cross n is a set of ordered pairs. X, Y, such that X is in N, Y is in N. Now we could write this a little without having to do so much writing. We could write this as X, Y are in the natural numbers. Okay, so let's list out some elements of this set. Before I do that, let's just remind ourselves that the natural numbers 0, 1, 2, 3, 4, 5, dot, 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 and so on. So infinitely many numbers in the natural numbers. They're all whole numbers. So you can think of it as the whole numbers including 0. Okay. So here we have ordered pairs. So let's see, what's a natural number? Let's pick 0. Okay. So let's say, what's another one? Okay, 0. That works. Now 0, 1. 0, 2. Now 0, 3, right? And we could just keep going like that. 0, 4, 0, 5, 0, 6, 0, 7. On and on forever and ever and ever. Let me list out another one. We got 1. Let's pick out, okay, so you have 1, 0. 1, 1. 1, 2. And so on and so on and so on. Let's see. Then maybe 2, 0. 2, 1. 2, 2. And you see how this goes. So lots, infinitely many ordered pairs in there. Excuse me. All right, so another way of looking at this is to think of it on a grid or on a XY axes sort of thing, coordinate axes, I guess that's what they call it. Okay, so let's see. Remember this was n cross n. We wrote them out like that. Another way to visualize n cross n is with graph like this. So you put the natural numbers as the x, natural numbers as y, and then we have 0, say 1, 2, 3, 4, 5, and so on. 1, 2, 3, 4, and so on. Okay, now I can't write them all out, but I'll write some of them. So we got 0, 0. So remember the 0, 0 was there. So we got 0, 0. Over 0, up 1. Over 0, up 2. 3, 4. Dot, dot, dot. Keep on going. Let's see. 1, 0. 1, 1. 1, 2. 1, 3. 1, 4. Dot, dot, dot. There, 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 there. And this just keeps going in all directions. Well, I guess over to the right and up. Okay. All right, so we have you might call that a lattice. All right, so that's n cross n. Okay, now we can look at this the graph of this in two ways. Let's see, the way that you saw in the reading, you can think of it as like a bubble diagram. You got n cross n over to n. I think I'm going to do this a little better here. Let's see. Draw the ordered pairs first, then put the circle around them. I think that makes sense. You're probably saying, where's the other ones go that I had down lower? Those are still there. I can put those in. So you got 0, 1, then we are 0, 0, then 0, 1, and then 0, 2, so on like so. And that's n cross n over to n. Let's see. So 0, 0, let's see if you think of this is 2 to the 0 times 3 to the 0. And you guessed it, that's 1. Okay, so this guy goes over to 1. Let's see, 0, 1, what does that go over to? Place that with a 1 there. 0, 1, that goes over to, okay, oops. 2 to the 0 times 3 to the 1, so that's 1 times 3, or 3. Goes over to 9. Okay, and there's lots of ordered pairs in here. Lots and lots and lots of them. Okay, something like that. All right. And I'll still show you how to fill in the table in just a second, okay? Make this a little smaller here. Another way you can think of this is instead of thinking of listing all of these, listing all of these in order like I'm doing here, or like in some sort of order, like I guess a natural order would be start with 0, list all the ones with 0 in the first coordinate, then go to 1, list all the ones with 1 in the first coordinate. It'll take, you'll be doing it forever, doing all the ones in the 0 with 0 in the first coordinate before you get on to 1 in the first coordinate. But theoretically, it's there is an order to these. You could define an order on these. Another way to see a nice order is to see some way to order them, is what I have here, what I've done already with this lattice or XY graph with the little red dots here. So you could think of this thing like I just did up top here, like I have right here, with a bubble diagram like they do in the Xi book. It's perfectly fine. You could also think of it like I have right here. Okay, and I'll show you that now. All right, so you have, this is your domain. This is your domain here. This is n cross n. And then your target is going to be the natural numbers. Remember, not everything in the target has to get hit for it to be a function. Okay, let's see. So 0, 1, 2, 3, 4, 5, 6. What are you doing? All right, so here we have n cross n again. And here we have n. We have our function f goes from n cross n to n. All right, so remember we just did, right? Let's see, 0, 0, that was the place of that's the place of the origin, right? Nothing new there. Remember that 2 to the 0 times 3 to the 0, that's 1 times 1 or 1. So think of it as this thing goes over to 1. Now let's see. How about this point? How about this point right here? Over 1 up 0. Right, let's see. F of 1, 0. That's 2 to the 1 times 3 to the 0. That's just 2. Okay, so this thing goes over to 2. All right, let's see. How about now looking at that point right there, over 0 up 1, that goes to 2 to the 0, 3 to the 1, that's 3. All right, so what we see here is that this goes over to there. How about 4? Does 4 get hit? Does 4 get hit? And the answer is no, right? Because if you think about it, 4 does not equal, oh, well, yeah, 4 does get hit, huh? 4 does get hit, huh? That's right. Okay, my bad. I'm sorry. 4 does get hit. I don't know what I was thinking. 4, so 2 to the something times 3 to the something. So does 4 equal 2 to the something times 3 to the something? Yes, it does, right? Yes, it does. Let's see. 4 equals 2 squared times 3 to the 0. Right, so that means over 2 up 0 goes there. So that means that this guy here goes there. right? Because this is 2, this is the point over x is 2, y is 0, so that goes to 2 squared times 3 to the 0, which gives you 4. Now what about 5? Now you see this is now you see with 5 doesn't equal 2 to the something times 3 to the something, right? There's no way you can get a 5 with multiplying any powers of 2 and powers of 3. There's no way you can get a 5, right? So there's no way you could put something in up there and get a 5 out. So nothing hits 5. Same thing for 0, right? Nothing hits that. Now what about 6? What goes over to 6? You guessed it. 1, 1, right? So 1, 1 goes over to 6. So 1, 1 there goes over to 6. Okay, I think we're ready to fill in the table now. Let's see, we said 0, 0, that went to, so let's see, 2 to the 0 times 3 to the 0. All right, let me write that out a little better. Let's see, that's 9 times 2 is 18. Let's see, that was a 4. Okay, when we take that out, oops. Say 2, 1, we got 2 and 1. So we got 3 times 4 is 12, and so on. Okay, I think you got the idea. That's what you got to do, something like that. Okay, now we want to say, okay, let's figure out, now let's figure out these right here. Let's figure out what goes there, there, and there. I'll show you how to do it. Then I think you'll be ready to fill out the table. Okay, so we have, so the way to think about this is we're looking for mn, right? They get sent over to 5, right? So that means that f of mn equals 5. Remember this is output here. This is the output, so mn is so when I say output, I mean the whole thing. F of mn is the output, whereas mn is the input. Right? Mn goes into the function, and out comes f of mn, which happens to be 5 in this case. All right, well, we're lucky we have a rule. We have a rule that we can compute with. This is 2 to the m times 3 to the n. And so now we ask ourselves, is it possible to find an m and an n that you can put into here and get 5 out? And the answer is no. So this does not exist there. Okay. All right, so you do the same with the others. Let's just look at that real fast. Let's see. Okay, well, I guess we'll start with 96. Start with 96. Let's see, that's 2. So I'm doing a prime factorization here. Let's see, that's 45, 46, 47, 48, 48. Off to the side, I could check with a calculator or, in my case, old school multiplication. 48 times 2, or let's see, 48 times 2, 8 times 2 is 16. 48, 9, that's 96. Okay, that worked. 48. 48 is 2. And what? That's 24. Yeah, that's 8. Yeah, that's okay. 2 and 12. Okay, we already saw that 12. Okay, yeah, let's see. So that's 4 and 3, 2 and 2. So 96 is 2 to the, let's see, 1, 2, 3, 4, 5, 2 to the 5th, times 3 to the 1. So over here you would write 5, 1. 5, 1. I assure you you'll have more room writing with a pen or a pencil. Okay, now let's just do 1,000. Is 1,000 going to work? So same idea, I'll do a prime factorization. Let's see. 1,000, is that? Thousand's definitely got a 10 in it, right? Let's see. Is that 10 times 100? Yeah, something like that. Okay, that's got a 5 and a 2 in it. Okay, you see that this got a 5 in it, right? So there's no way you can write it like that. So there's no way you can write it. It's got a 5 in it, so it's got a prime in it other than 2 and 3. So does not exist. All right, good luck.